All right, folks. Oh my goodness. You need at least half a sheet of paper. Give me a second. Okay, read that problem. We're going to do this together. This is our first ice table problem. Oh my goodness. All right. We are in for it now, folks. We got an initial concentration of everything. And I want to know at the end of the day, how much of each of these is going to be left when the reaction's done reacting if it has an equilibrium constant of 0.36. We got a lot of steps. The first thing that you need to do is write the mass action expression. That's always the first thing that needs to get done. So why don't you write the mass action expression for this reaction? Go ahead, Kc equals, do that for me. All right, so concentration of NO2 squared divided by the concentration of N2O4. That's my mass action expression. Now here's the problem. I need to know where I'm at. I'm given these initial concentrations. So I need to know, am I already at equilibrium? That would be great. That's not going to happen. Or does the reaction need to consume product, make reactant, or does it need to consume reactant, make product? So in order to figure that out, we need to plug these initial values into the mass action expression. And when you are plugging initial values into a mass action expression, you are solving for the reaction quotient. So now I want you to plug those values in, and I want you to solve for the reaction quotient, and I want you to predict what direction this reaction is going to go to reach equilibrium. That's the next step. So we wrote a mass action expression. Now we're figuring out what direction it's got to go. And because we're not missing something, we got to solve for a reaction quotient. Go ahead and do that. All right. I got a reaction quotient of 0.025. Check yours. Hopefully you got a 0.025 too. Now, because this is like a snapshot of where the reaction is right now. And what we know is it is not at equilibrium, because the equilibrium constant that was provided says this reaction, when it's at equilibrium, when you plug that junk into the mass action expression, you should get 0.36. We didn't get 0.36. What do we get? We got a value where Q is less than Kc. And I am telling you, I do not have this memorized. I stop and think about it every single time. I refuse to memorize it. I always stop and I say, okay, at the end of the day, it's product concentrations over reactant concentrations. My value right now is too small. It's got to get bigger to reach equilibrium. How do you make it bigger? We got to grow the numerator, shrink the denominator. This reaction is shifting right to reach equilibrium. Shifts right. What does that mean? That means in order to reach equilibrium, this is going to go down by some amount 1x. And this is going to go up by some amount 2x, because as the coefficients tell us the ratio of the amounts that this way. For every one of these that gets consumed, we make two of these. So if this is going down by some amount x, this is going up by 2x. Once you know the direction that the reaction is going to reach equilibrium, it is now time, once you know the direction the reaction is going to go to reach equilibrium, it is now time to make an ice table. Now, I make my ice tables a little differently. I write ice going across. A lot of people write ice going down. It's totally your call, but I'm an across guy. So if you start watching some Khan Academy stuff or something, their ice table is going to be flipped. Your call. I don't know. I've just always done it this way. So it's just how I do it. I don't care. Anyway, here we go. So we're going to write, I like to write ice across the top. So I, C, E. And again, that is an acronym. And then each thing that's in your mass action expression gets a row in the ice table. So we only have two things. So our ice table is only going to have two rows. So N2O4 gets a row in our ice table, and NO2 gets a row in our ice table. Okay, so make that. Take a second, catch up, make your ice table. All right. So the N2O4 concentration is 0.100. The NO2 concentration is 0.0500. I stands for initial. So what are the starting concentrations? So the initial concentration of the N2O4, 0.1, and the initial concentration of the NO2, 0.05. C stands for change. What amount are these things going to change? Well, since we determined the reaction is going to go right to reach equilibrium, then this reactant has got to go down by some amount x, so minus x. And this product is going to go up by some amount 2x plus 2x. So again, the C stands for change. How much is everything going to change by? Finally, the E stands for equilibrium. And that says once we're at equilibrium, what is the concentration going to be? Well, here's what we know. The equilibrium amount of this is going to be the starting amount plus or minus the change. So at equilibrium, the amount of N2O4 in there is going to be 0.100 minus X. And the amount of NO2 in there, we're just combining the I and C columns here for the E column, is going to be 0.0500 plus 2X. What we have now done is by defining the initial concentration, by determining it's going this way and it's going to change, but these are going to change by this, we have now defined the equilibrium concentrations in terms of X. And now what we can do is this. We can now plug these equilibrium concentrations into the mass action expression and then solve for X using the magic of algebra 2. I know what you're thinking. I didn't think there was actually a use for algebra 2. Neither did I when I was taking algebra 2, but there is a use for it, right? The most algebra 2 total waste of your time, but that whole factoring and the foiling and the quadratic formulas, that stuff's actually useful, and that's the stuff we're going to need here. So let's break this down a little bit. Let's recap right to where we are right now. We first wrote a mass action expression. Then we determined what direction the reaction was going to go to reach equilibrium by solving for a reaction quotient, comparing it to the equilibrium constant. Then we made an ICE table. We put in the initial concentrations. We said how much everything was going to change by, and we said at equilibrium, you're going to combine the I and C columns to have the equilibrium column. Now what you need to do, these are the equilibrium concentrations in terms of X. So we're going to plug them into the mass action expression, and we know the equilibrium constant, and then we are going to have to do some math. Woo! Here we go. The equilibrium, so I'm going to get rid of this reaction quotient just to give me some more room. The equilibrium constant is 0.36. That was provided. That's going to equal the NO2 concentration. That's 0.0500 plus 2x, and that gets squared, divided by the N2O4 concentration. That's 0.100 minus x. So this is what we have got. Cool. Now, if you are a math whiz, you are probably looking at this and you're probably seeing we are in for some trouble. Our goal is to be able to solve for x. Okay, and if we can get x, then we could plug that x value into here and solve for the equilibrium concentrations. How do we get x? It's going to take you about half a sheet of paper. Okay, here's what we're going to have to do. We need to combine like terms and all that jazz. Here's the problem. 0.0500 plus 2x quantity squared. How do you get that? Well, that's actually 0.0500 plus 2x times 0.0500 plus 2x. Right? I mean, let's go back to algebra 2. When you have some quantity squared, it's actually like it times itself, right? So now in the numerator, I got the quantity 0.0500 plus 2x times quantity 0.0500 plus 2x. What do you got to do there? You got to FOIL. So we got to FOIL the numerator, right? First, outer, inner, last. Okay, and if you've forgotten how to FOIL, okay, I got it on the next slide here. FOIL, first, outer, inner, last, okay? So why don't you try to FOIL that numerator? I'll give you a minute. It may have been a few years since you FOIL. I don't know. Maybe it was last week. I got no idea, like how long you've been away from Algebra 2. But try to FOIL that numerator, and then we'll talk. All right, folks, hopefully what you got when you did the first, you got 0.0025. When you did the outer, you got 0.1x. When you did the inner, you got 0.1x. And when you did the last, you got 4x squared. Now I'm going to combine this, and I'm going to rewrite it because we're eventually going to need to do the quadratic formula. I'm going to rewrite this really quick as 4x squared plus 0.2x plus 0.0025. So I'm going to rewrite this as 4x squared plus 0.2x plus 0.0025. Just like that. All right. Now what do? Well, we have got a quadratic now at this point, which means we are going to need to use the quadratic formula to solve for the x values, the two possible solutions at x. One of them will be valid, one of them will be invalid. It's very easy to tell which is which. Anyway, how do you use the quadratic formula? Well, you got to get the whole polynomial, the whole quadratic, set equal to 0. So we got to get this 0.1 minus x out of the denominator, and then we'll have to distribute, and then we'll have to, oh my gosh. So the next step is we're going to multiply both sides by 0.100 minus x. I'm now going to distribute the 0.36 in. Okay, so hopefully you can follow me there. We get 0.036 minus 0.36x equals 4x squared plus 0.2x plus 0.0025. Now we need to get everything equal to 0. So we are going to subtract 0.036 from both sides. And we are going to add 0.36x to both sides. And we are going to get 0 equals 4x squared plus 0.56x minus 0.0335. Now I'm going to give you a tip here, folks. Don't try to do sig figs here. Just keep a whole bunch of the numbers, because if you start rounding, man, that drastically affects the quadratic, right? When you plug the numbers in. So don't worry about sig figs till the end. Like try to keep, don't round that to 0.034, right? Try to keep the values in there. So now we have our quadratic equal to 0, right? And that is important. Why is that important? That's important because now we can use the quadratic formula. And if you forgot what the quadratic formula is, well, don't you worry, I got it there for you. It is negative b plus or minus the square root of b squared minus 4ac over 2a, right? Where a is the number in front of the x squared, b is the number in front of the x, and c is the is what's after the x there in the polynomial. Okay, so you need to take this value. You're going to plug the 4 in for the a, the 0.56 in for the b, and the negative 0.0335 in for the c, and see if you can't solve for x. If you listen, try it. Try to plug in what we just got, okay, and solve for x. Worst thing could happen is you could get it wrong, and I'll walk you through the correct solution. So I'm actually going to erase all this jazz. So just so you can kind of check your steps as you go, like check in. This is what it should look like once you plugged it in. Negative 0.56, that's negative b, plus or minus the square root of b squared, 0.56 squared, minus 4 times a, which is also 4, times c. Watch out, it's negative 0.0335 all over 2a, so that's 2 times 4. Okay. Keep going, folks. If you did it correctly, you should get x equals positive 0.0453 or negative 0.185. Negative 0.185. So I tried to break it down as simply as possible. I like to get what's under the radical and like all like before, so that's all this 0.56 squared minus 4 times 4 times negative 0.0335. That's 0.8496. Then we take the square root of that. That's 0.922. So negative 0.56 plus 0.922 divided by 8, that's positive 0.0453. And negative 0.56 minus 0.922 divided by 8, that's negative 0.185. Now, this one is easy. When you do the quadratic formula, you are always going to end up with 2 solutions. Okay? And sometimes it's harder than others to figure out which one is the correct solution, but this time it's easy. If you ever get a negative solution of the quadratic, that cannot possibly be the correct solution. The correct solution is the positive value, so 0.0453. Now, at this point, it feels like you're done because you just did a heck of a lot of work, right? But you're not done. You're almost done. To refresh your memory for the problem, because it feels like a lifetime ago, in this problem, come on now, we want the equilibrium concentration of each species. How much of this will be left at equilibrium? And how much of this will be left at equilibrium? How do we get that? Well, now that we know x, we're going to plug this in and solve for the equilibrium values of each. So here we go. 0.1 minus x, 0.0453. That'll be 0.0547. Probably need to stop at the thousandths place, so 0.055, according to addition, subtraction, sig fig rules. I'm going to give you a plus or minus a sig fig on a problem like this. And then here, 0.0500 plus 2 times 0.0453, that's going to be 0.14, we'll do 1, as our equilibrium value for NO2. That is a lot of work. Now, we can sometimes take a shortcut. You actually could not take the shortcut in this problem, but you can sometimes take a shortcut. It's going to make the problem slightly smaller where you can avoid the quadratic formula. I'll teach you that after the break. It's going to be called the x small assumption. Okay? But when you do all this work, I highly, highly, highly suggest that you check your answer at the end. So I would not be done yet. I would, if it was me, still want to check my work because there's so many little places that I could have gone wrong. A common mistake people make, they don't bring that negative with the 0.0035 or with the negative 0.0335. They don't bring that negative along into the quadratic. So how can you check your answer? Well, here's what we can do. We know the equilibrium constant is 0.36. So if we plug these equilibrium values into the mass action expression, we should get 0.36 if we did this correctly, right? If these are truly the equilibrium concentrations, then we should get the equilibrium constant if we plug them in. So let's check our work here. So we're going to do a little check. Check. If we did this correctly. So we're going to plug in the NO2 concentration. That's so Kc equals 0.141 squared divided by the N2O4 concentration, 0.055. And hopefully we get 0.36. If we don't, I'm going to be really sad. And we get 0.36. It checks out. We are golden. Oh, yeah. This stuff just got way harder, right? I mean, it's legit, right? There's a reason you had to take Algebra 2 before you take Chem 102, right? And it's this. Okay, let's stop and really think about what we did here. We took initial values. Like, here's what we're going to throw this in there. We're going to seal it up. And just because somebody's done this reaction before and they've told us the equilibrium constant, we can predict what the equilibrium values will be when the reaction has reached that dynamic state. That's pretty powerful. It's like predicting the future, right? If you know the equilibrium constant for a reaction, you can take any starting amount of reactants and products and predict how much will be left when the reaction reaches equilibrium. You can predict the future. Now, again, we know nothing about how fast the reaction goes. This tells it like how long it's going to take. I got no idea. But when it reaches equilibrium, there'll be this much NO2 in there, and there'll be this much N2O4 in there. And these are, by the way, concentrations. So they are molarities if you were looking for a unit for that.